of this that's possible. So let me go ahead and introduce Kris. Dr. Kris Karnauskas is an associate professor in the Department of Atmospheric and Oceanic Sciences at CU Boulder, a colleague of mine at Boulder. He has secondary appointments at the CU School of Medicine and the Colorado School of Public Health. Prior to joining CU in 2015, he spent 6 years at Woods Hole Oceanographic Institute and their joint program with MIT. Also spent time on a Sloan Foundation sabbatical at a research unit in Paris. So Kris actually teaches this Climate 101, we're calling it, within the context of the CU Boulder curriculum. It's a fundamental for students that are majoring in atmospheric and oceanic sciences. So we're very fortunate to have him here to offer a shortened version of his lecture. So Kris, I'll go ahead and hand it to you.
Thank you, Lori, and hello, everybody. I want to underscore what Lori said. This is not some research talk where I feel the need to get all the way through every slide and every point that I want to make for my own good. Think of it as a class, and if you have any questions midway, just raise your hand, or if I'm not noticing the hands or something, just jump right in. So, yeah, we'll do a whole semester worth of Climate 101 in about 40 minutes. How does that sound, everybody? Let me share my slides here. I love cracking jokes on Zoom when I have no idea how it landed. All right.
You
This may
got a
take
bunch
me
of
just a
thumbs up.
second to arrange my
I like it a
monitors
lot.
and yeah. All right. Can somebody tell me if like you see the full screen
It looks
stuff?
good, Kris.
All right, cool. And I can still see my Zoom window as well, so I should be able to tell if people have questions or something. Okay, so yeah, I was tasked with talking about Climate Systems 101, and so I want to talk a little bit about some of the nuts and bolts of climate change, and then a couple studies of mine that for just for fun, because I know it's a little closer to the work of the folks in this audience. It's about how it impacts human health. So let's talk about greenhouse gases first. Okay, so we've been measuring greenhouse gases from on top of Mauna Loa since 1958. NOAA's been doing that at the Mauna Loa Observatory. And I want to start with this slide that has three graphs on it because I think that these are the three most important graphs that tell the story of carbon dioxide. And I promise most of my slides will not have multiple graphs, more like one, but upper left-hand corner is emissions. Are you able to see my cursor when I point at stuff? Okay, thanks. So these are emissions, and I want to make an important distinction here between emissions and concentration. Sometimes we talk about CO2 and we don't distinguish between the two. It's very simple. It's kind of like a bank account. Emissions are your annual deposits into your account or withdrawals, which is hard to do with CO2. And the balance is like the concentration of carbon dioxide. So these are the deposits. This is how many, gigatons of carbon that we're putting into the atmosphere over the years, starting in 1960, and it's been going up. And you can see that as in, whether it's intentional or not, humans do have a hand on the dial when there's major economic crises, or, for example, the COVID-19 pandemic. You can see that there are noticeable dips in the emissions. I find this graph really frightening because we all think back to how, you know, tragic COVID-19 was and how our entire lifestyle and our ability to, frankly, our ability to do anything that emits carbon dioxide seemed to come to a grinding halt for a while. And yet the emissions really only dipped by, a couple percent that year. Fast forward, this is the annual increase in the concentration, but that kind of leads us to this. This is the concentration. So again, deposits into the account are up here, and this is the balance in the account. If it's a bank account, you can see it went up past 420. It was about 425 parts per million back in last year in 2024. And if you go looking, this is why it's an important distinction between emissions and concentration, because yeah, there's a dip in emissions, but it was a dip from like, 9 to 8.5 or something like that, you're still putting money in the bank, so the balance went up. You can't really see a dip in the concentration even from COVID here, in the concentration. So we're going to talk about the greenhouse effect in a second here, and I wanted to open with carbon dioxide, but since we are
Oh,
in, sorry, yeah,
Kris,
go
can
right
I
ahead.
just pop in and ask a question? This is
Yeah,
Deborah.
please.
I stuck it in the chat, but the last graph you just showed us, those are actual observations, correct?
Yeah,
That's not like, mhm.
this one.
Yep,
Yeah, those are made by people who are born and bred to measure carbon dioxide, with actual careful chemical measurements. Yeah.
right. Okay, great. It just
Yeah.
helps to understand what's being measured, and so that's great. Thank you.
How about this? I promise you that when I show a model result, I'll give a loud and clear, you know, warning that we're transitioning from anything in observation world to models, because I think that's really important, Deborah. Thanks
Thanks.
for,
That's great. Perfect.
yeah.
Thanks a lot.
Chris, is Mauna Loa's funding at risk?
Yeah, probably. Um, I
That's what
don't
I thought
really,
I read. I wondered if you had heard. I mean, this really underscores the importance of that monitoring.
I looked I looked last night, when I'm as any self-respecting professor is preparing their slides the night before, it was there and the measurements were being made as of yesterday. So they're still there. But within the
Fingers
next
crossed.
couple of months, I think we'll learn more about that and a lot of things in NOAA. So yeah, thanks. Pile it on to the depressing news that you're about to see. So let's take a big step back. Okay, this is I like to think really long term when you're sort of trying to grasp the scale of the problem that we're kind of living through right now in terms of climate, um, in a really long term, pre-human sort of perspective. And for that, we go to Antarctica. We go to Antarctica because what we can do is drill down into the ice. The ice is like a time machine or a time capsule, okay? So every year another layer of ice is formed through snowfall and precipitation on top of the Antarctic ice sheet, and when that does, it traps in these tiny little air bubbles, whatever was in the air the day that ice was formed. So it's like drilling back into time, and we can very carefully extract the little air bubbles out of the ice core. And we know, just by essentially counting the layers going down, kind of like tree rings, you can tell what the carbon dioxide in the atmosphere was a really long time ago. Almost a million years is how much time we've recovered from Antarctic ice cores. And this is what that looks like. So this is a graph of, again, it's another graph of carbon dioxide concentration, and this is not from a model. These are from actual measurements of carbon dioxide in the air bubbles in a set of really long ice cores from Antarctica. And it shows you the glacial, interglacial swings that the climate has undergone over and over the past, this is 800,000 years, almost a million years. And what you can see is this sort of in and out, slow in and out of, when it's down low, that's an ice age. So, like the Laurentide ice sheet would have come all the way down through Minnesota and Iowa, and the world would look like a very different place. We happen to be lucky enough to be living in an interglacial right now, which means we're not in a glacial, it's in between glacials, and we're somewhere on the high end of it. So notice that the scale of it is like 100 parts per million. If you can read these numbers on the y-axis, it's like around 200 parts per million during a glacial period and around 300 parts per million during an interglacial. So that's a lot, 100 parts per million is a lot of CO2. Fast forward let's add a little bit to the graph. Okay, so 317 parts per million was observed in 1960, around the time that the Mauna Loa Observatory got going. And in 2024, it was 425. So just look at this for a second and see, if you're seeing it like me, I look at this and say, wow, we've already added a whole glacial amount worth of CO2 to the atmosphere. We've sort of taken ourselves into a whole new territory, and we know what's happened. This is observations of surface temperature change. It's just a little um, icon sort of level. We know it's warming. It's not warming the same everywhere, but it's warming, and I'll explain that why we know why that's because of the CO2. But the future is uncertain, right? We can measure CO2 in the past, and we can, try to predict a lot of things about the future, but carbon dioxide in the future depends on a lot of things we don't know enough about. We don't know, and this is probably a lot of this is as in the collective you on this call, your wheelhouse. How is population going to evolve? How is geopolitics and technology and all sorts of societal aspects? That's really what's going to drive whether the future looks like this, which is like the low end carbon dioxide concentration by the year 2100, whether it looks like this or the business as usual classic, we call it RCP 85, but I don't have time to get into all that. The high end emission scenario that scientists are actually working with has us at 930 parts per million by the end of the century. So again, I'm adding it onto this same graph as CO2 over the last almost a million years so that you can see this is all to scale. This 930 is 930 on the exact same graph that the glacial interglacial swings of CO2, which were bouncing around between 200 and 300. And just again, think back to how different the world was between 200 and 300. It's an ice age or it's not. That's a huge difference. We're going to be facing some pretty unprecedented climatologically speaking times in our lifetime. All right, there's that. It's very frightening, and I'm sorry to lead off with something like that, but it does motivate, hopefully, you wanting to learn a little something about the greenhouse effect. So let's start with something kind of basic, although it's actually a pretty, the more you dig into this, this is a pretty sophisticated topic. But, what governs whether the world warms or cools or how much it warms? It's really just about whether there's more energy being held in the system or more energy being released from the system. It all goes back to laws of thermodynamics that sound more complicated than they really are, but here's how this works. So if we stuck a satellite that orbits the Earth, outside of our atmosphere, and we pointed it at the sun, it would give us a map that looks like this. It's very simple. It says that the tropics receive lots of radiation, lots of solar radiation from the sun, and the poles receive very little. And that's actually pretty simple. Why? Because the planet is a sphere, the sun is really, really far away compared to the size of the Earth. So those sun's rays, they come in all at like these parallel angles. So up at the poles, it's spread out. That one ray of sun is spread out over a big area, and on the in the near the equator, it's just hitting dead on, kind of like if you were to do the trick that teachers do with shining a flashlight at a globe. You shine it right at the equator, straight on. It's all concentrated there. If you move it up to the pole, has to get spread out. So that's a pretty simple map. That's how much energy is coming in. And then the energy that's going out, if we were to magically take that same satellite and flip it around and point it at the Earth, and instead of measuring the radiation from the sun, we're measuring the radiation from the Earth, it's less. It's a little more complicated pattern because it depends on where the clouds are. You're going to get a lot of heat coming off of, say, the Sahara Desert because it's really hot and it's good at emitting that heat. But anyways, you take the difference of these two maps, and this is it. So notice that like in the tropics, the colors are red. And what that means on my color scale is that the tropics are on balance receiving more energy than it's losing. Okay? So it's getting a lot of sunlight and it's not radiating as much back to space. The poles, it's the other way around. In fact, where I live in Colorado, we're just on the other side of that zero line, which means right here where I am right now, on average over the course of the year, I'm at we're actually losing more energy than we're gaining. So what do you think that means? I'm asking an open question for anybody on Zoom here. We've got the tropics that are receiving more energy than losing, and the poles are losing more energy than receiving. Why isn't the equator continuously getting hotter and hotter and hotter every day and became unlivable a long time ago? What is this, what does this map of this energy imbalance mean to you? What do you think is going on?
The heat goes from the equator up to the poles?
Exactly, Jason. Something has to be moving that heat from the equator to the poles, and that's our weather. That's literally the climate moving things around. The ocean does a good chunk of this, the atmosphere does a good chunk of it. Have you ever noticed that a lot of things in the atmosphere tend to spin? Whether you're talking about a hurricane or a very large scale weather system that's just kind of moving across the continental United States, there's like a rotation to that. And that rotation is kind of mixing that hot excess energy up to the pole and some of that cold air down towards the tropics, so that our weather is doing the job of that. Okay, so we have to have an atmospheric circulation, and now you can kind of see that it's all about the difference between input and output of radiation. So let's go to the greenhouse effect, because what the greenhouse effect is essentially, how are we changing that? Because prior to humans coming along and emitting carbon dioxide and other greenhouse gases into the atmosphere, there was about the same amount of energy coming in as out overall, which means the temperature of the planet as a whole, averaged over the whole surface of the planet, was in an equilibrium state. It wasn't moving, it wasn't going up or down. Lori.
Well, there's an interesting question in the chat that I'm relaying.
Oh,
So,
I am not seeing the chat,
no, no,
so
no,
fire
no,
away.
don't worry. I can raise my hands. But Sam, the idea that this weather is circulating, the different temperatures around, is Sam McTavish asked, does that trigger more severe
Ah,
extreme weather events? Is that part of what's happening there?
that's a great question. It's also a really complicated question, but my answer to you is yes. I mean, it kind of makes sense that the stronger this imbalance is, the more the weather has to be crazy in order to work to alleviate that big gradient. Nature does not like gradients. It doesn't like too much of something here and too little here. It wants to even it out. So I would say yes. That's a very complicated question though. But overall, I think that's a really great start to like 10 PhD theses with that question right there.
Thanks, Chris, and thank you, Sam, for the question.
Yeah, thanks, Sam. Now I have the chat window open on my other monitor so I can see it. But anyway, you've all seen pictures like this. You're probably too smart for this, so I'm going to take you like one step further to give you a little bit more of a kind of under the hood understanding of the greenhouse effect. And honestly, it's not that much more complicated than this. I love the analogy of blankets and actual greenhouses. It's fine. But here's kind of like the first step in thinking through this. This is wavelength of radiation on this graph. So like the sunlight, the visible light and solar radiation coming from the sun, we call that short wave. All right, because it's got like a short wavelength. The waves are literally the invisible waves are like actually short. And then you have long wave radiation, and all that means is heat. So, like, if you are standing close to a radiator in an old house on a cold day and you can feel the heat from the radiator, you're feeling long wave radiation. Or infrared or thermal, there's a million names for it, but that's what that is. So, the Earth picks up all of this solar radiation, it heats up the surface, and it's important that these are two separate things, then the surface of the Earth emits the long wave radiation, presumably all the way back out to space, unless things reflect it or greenhouse gases absorb it. But you get the idea. Solar in, heat out, short wave in, long wave out. They're different wavelengths. So if you look at a molecule, I'm not a chemist, so this is as far as we're going into chemistry. But if you look at a molecule of carbon dioxide, you've got this one carbon and two oxygens. And if you had one of these in your hands and you could play with it like a toy, you could do a couple things with it. You could pull on the oxygens and stretch those bonds. And that takes energy, doesn't it? I would be exerting energy of my own to do that. You could also kind of bend them, and that would also take energy. And it turns out the chemists have figured out when a carbon dioxide molecule, for example, stretches, that absorbs radiation at a certain wavelength, and the bending absorbs that at a different wavelength. But like, I'm just showing you this to imply that we definitely know that greenhouse and why greenhouse gases are so good at absorbing this long wave radiation that's trying to leave the Earth. Okay, so they do this for sure. So let's go to back into a schematic of the Earth and the greenhouse effect. This is the way I explain it to people literally of all ages. I think it's the one that works. Happy to share my slides if you ever want them. Here's the Earth and here's the atmosphere. Here's that solar radiation coming down from the sun, heating the surface of the Earth. And here's that long wave or infrared energy leaving if it's coming from the surface. So, humans, prior to humans coming along, you've got the same amount of energy coming in and as is going out. And so you eventually will reach this equilibrium temperature. It'll actually be too cold for us to really enjoy. Now, remember that the amount of energy that's released by an object is actually related to its temperature. Okay, so again, another reference to COVID, but do you remember all of the infrared thermometers that nurses and, sport coaches had? They would point an infrared thermometer at your forehead. All that's doing is measuring this red line here. It's measuring the amount of infrared radiation leaving the surface of your forehead, and then it's just using a very simple equation to convert that into a temperature. It's sigma t to the fourth power, if you've ever heard of the Stefan Boltzmann law. But anyway, that's all that is. And so the hotter something is, the more it emits. Well, think about the atmosphere. Have you ever seen, a day like this? Obviously not from this high unless you're in an airplane, but there seems to be a lid, doesn't there? Like sometimes these big towering clouds will hit an invisible lid and start spreading out. They kind of look like an anvil, if you've ever seen that before. And that's because there's a boundary between the lowest layer of the atmosphere where temperature decreases with height and then it increases with height. So clouds can rise as long as, it's decreasing with height and then it stops because it's too stable. But anyway, the point is temperature decreases with height. So when we put carbon dioxide in the atmosphere, where do you think it lives? It doesn't just sit on the floor. It hovers all around the lower layer of the atmosphere, here in the troposphere where we're emitting it. That means it's colder because it's not down here at the surface where it's the warmest. Okay, so now instead of the surface being the last thing to emit the radiation out to space, it's actually something that's colder. It's the greenhouse gases. So since it's colder, it emits less radiation, and now we have an imbalance. We have a problem. We haven't changed the amount of solar radiation coming in, but we have changed the amount of long wave radiation going out, and that means the temperature has to go up. So that's the greenhouse effect. We can measure this from space. There have been observational studies that have actually tracked the solar radiation coming in and the long wave radiation going out from satellites over many decades, and we can tell that these numbers are changing, and they're changing. We can even look at the fingerprint of those, again, where in sort of wavelength space are these changes happening, and we can unambiguously fingerprint it right back to carbon dioxide, methane, and other nitrous oxide, other greenhouse gases that we know about. So let me just stop there for a second before a little transition here. And okay, I see Lori, you asked, is the shortwave being converted to long wave? How? Yeah, so this happens to you when you stand outside in the sun. You go outside, the shortwave radiation hits your body. If you're wearing a black shirt, it's going to absorb a lot more. You all know that. And then it is being emitted as heat. So your temperature goes up, and the more your temperature goes up, the more heat you release. So it really is like a two-step process. It's not the same as reflecting solar radiation. If you have like a white shirt on, that's actually going to reflect a lot. That's not the same as absorption and re-emission. Good question. Are there any other greenhouse gases? Yeah, so we all like to rag on carbon dioxide. The main reason that carbon dioxide is usually talked about the most is that it's the most abundant by a long shot. Methane, pound for pound, is actually, I think it's about 20 times more potent of a greenhouse gas as carbon dioxide. But the problem is with methane, or I guess a good problem, is that there isn't as much of it. So they kind of like CO2 is the little one, but there's a lot of them, and methane is the really strong one, but there aren't as many of them. Also, when we put CO2 in the atmosphere, it's there for thousands of years. Methane will come out in like 10 years. It'll
Are
the
things
processes will.
other than greenhouse gases that have the same effect?
Oh, things other than greenhouse gases. Um, no, I would because if they did have that effect, I would call it a greenhouse gas. But that's the
Right,
so
okay.
like water vapor, for example, is a really effective greenhouse gas. It's a natural greenhouse
I
gas.
missed that. What is?
Water vapor.
Yeah, okay, okay, but you'd still call it a greenhouse gas.
Water vapor is a
Yeah,
greenhouse gas
yeah.
because it does try to absorb radiation that's trying to leave the earth. Yeah, so if you live like on the coast, say California, where the prevailing winds are coming from the Pacific Ocean, um, your nights are warmer, aren't they? Like it doesn't drop down as much. A lot of that has to do with the fact that you've got this kind of overnight greenhouse effect keeping it in check. Yeah.
I didn't
You
mean to
had
do
a
that, but sorry.
you had
There
a
was
plot earlier with the carbon molecules that I think was related to how they were bending and the length of, was it related to the length, the wavelength
yeah,
of
it's more that like different dance moves, as I would call them, are they will absorb radiation at different wavelengths. So like let's say 100, this little graph right here is like 100% of the radiation being emitted by something along these wavelengths. The stretching part absorbs like at 2400 of this wave number. It's a one over the wavelength, but anyway, and then the bending does it at a different place. Methane, I've got like a backup slide somewhere here. I thought no one's going to ask about methane, and I've got way too many slides, so let me not include that. Of course, there's plenty of interest in methane as it turns out. So look at the methane molecule. There's a whole lot more things that it can do. There's a lot more dance moves that it's got. Okay. And so that's why pound for pound, methane is a lot stronger. It's, let's see, 25 times the global warming potential or the ability to absorb radiation. But the concentration is nothing compared to the concentration of CO2. So they kind of like balance out a little bit. The big one is the lifetime in the atmosphere. The lifetime in the atmosphere of methane, there's processes in the atmosphere that bring the methane out within like 12 years on average, but thousands of years when you emit CO2, it's there. So hopefully that helps to answer that.
but that's not related to the solar coming in and the heat going out.
It's related to the heat going out, but it's not related to the solar
Solar
coming in.
coming
So
in. Okay.
these things don't absorb methane and carbon dioxide. They do absolutely nothing to the solar radiation coming through the atmosphere. It's only the long wavelengths, the heat that's leaving the atmosphere that's able to be absorbed by the CO2 and methane.
Got it. Thanks, mate.
And that's why a greenhouse, isn't that like that kind of goes back to why we call it greenhouse, right? Because if you're in a greenhouse, you're going to feel the sun, if those window panes are clear. Um, but the long wave radiation that's trying to leave, like you feel warm in a greenhouse on a sunny day or a sunroom attached to your house, same thing, right? You're going to feel warm in there because it's trapping the energy. And it's actually the outermost layers of your windows. Those are the things that are emitting the radiation, which is not as warm as it has become inside because of the sun coming in. So, anyway, a greenhouse is actually a really great analogy for this. Okay, so I'm rapidly running out of time. Let me show you maybe just like one or two cool things that ways that we're observing the climate system, and then give you a little teaser of like one of my health studies here. So we all know the surface is warming. For example, here's the latest map from NASA of the change in surface temperature where it's gray. We just didn't have enough thermometers to confidently calculate the trend. But anyway, you can see what's going on over the surface ocean. The surface. The ocean covers 70% of the planet's surface. And so I think the ocean's really important. And you may not know this, but we've got a really neat way of observing the heat changes in the atmosphere. And they're floats. This is this thing that I don't know why they're throwing it off the side of like a 20-meter deck of a ship. You're going to break this thing. This is not how you deploy one of these. You're supposed to carefully lower them over the side of the boat. But anyway, this is called an Argo float, and they float around in the ocean going up and down, and they're measuring the ocean. Take a wild guess. How many of these do you think are out there today? All over the world ocean. How many would you guess? Don't let science funding taint your guess by too much. But what do you think?
500.
I'm glad somebody guessed something so low. It's 4,000. We have four. In fact, this is from today. So all of those black dots are a place where within the last 30 days, a float has transmitted data back to our home base, via satellite. They basically have phones on them, like satellite phones. So when they pop up to the surface, they send their location and all the data back. 4,156 floats have returned data in the last 30 years. This is like a revolution in my world. Yeah, they're funded internationally, for sure. Yeah, it's an international Argo program. Anyway, that lets us do something way more, I think, compelling than just like the surface temperature, because the climate's a really big thing. And where do you think all of the excess heat in the climate's being stored? It's being stored in the ocean. If you ever tried to, well, of course you probably have, boil a pot of water. Big pot of water, it's going to take you like 15 minutes to boil that big pot of water, right? That's because the ocean can absorb heat for a long time before its temperature goes up. So this is like the big battery. It's like the capacitor of heat. And so we've calculated how much heat, and it's not in terms of temperature, it's in terms of heat content in this obscure unit, zeta joules, but joules is a unit of energy. Anyway, it's going up. Doesn't matter if the Chinese team analyzed it or the US team analyzed it in different ways, it's going up by a lot. And so if the heat of the ocean is going up, we can make a nice touch point to society because, nobody really feels the heat content of the ocean. But what do you think happens to the ocean when the heat content goes up? When it warms up, what would you say happens to the whole thing? More evaporation? Yeah. Yep. What else? It wasn't the thing I was
It
hoping you would guess,
expands.
but that's a correct answer.
It expands.
It expands, exactly. So we can measure that too. This is a satellite called an altimeter. Altimeter, like the root word of it is altitude, right? Excuse me. So this altimeter satellite goes over the ocean surface and it bounces a little beam of energy off the surface of the ocean. And that beam comes back, and we know exactly how fast that beam moves because it's just the speed of light. So if you have a very expensive, precise clock like NASA would have, you can measure the time it took that beam of energy to hit the ocean surface and come back up, and there, voila, you have distance. Distance is speed over time, right? So we can measure sea level rise from this. And so we know that the sea level has been rising by a few millimeters per year since we launched these satellites with very little variation. That orange curve is the satellite data. The blue curve is from tide gauges. So tide gauges are a bit tricky because the satellite observes the whole ocean, and that's great. But we've only been doing it since 93, so wah wah. But the tide gauges have been in major cities for hundreds of years. And so that's great, but they're only measuring it in those one location. So there's a whole cottage industry in my field of oceanography that tries to take those scattered points from like the old cities and interpolate to the whole ocean, which is a really dicey business. But we can see that at least over the last few decades, it does match on pretty well. And this is like our best estimate of how sea level has varied going all the way back to the beginning of the 20th century. So the sea level is obviously going up. All right, that's just one symptom. I'll spend just a few minutes. Let me pause. I should do that before transitioning, as this is a class. Any questions about, these physical symptoms of climate change, how we sort of link it to carbon dioxide? I've skipped some things, so if you feel like you missed something, it could be in there. Any questions
Tide
before going
gauges
on?
in the city? I mean, just out of human curiosity over the course of centuries?
Sorry, Lori, I had to hit my volume to bring you up. I heard
Oh, don't worry.
human
The tide, you
curiosity.
mentioned that tide gauges have been in cities for hundreds of years. Is that just human curiosity over the centuries?
I see. There's also a very practical, you know, there's other motivations to measure sea level rise than thinking ahead to climate change or just being curious. You're literally learning about the tides, and so that has a big impact on coastal navigation and maritime navigation writ large. So I think
Fisheries, right?
yeah, that's probably where that interest came from in the beginning. I don't think like in 1880 they were like, well, we might be in
Yeah.
this climate crisis in 2025. Like, we
No,
better
no,
start.
no, absolutely. But it's interesting to think about, yeah, different motivations, but the data is so useful now.
Yeah, exactly. Yeah. And we're again, another whole cottage industry is kind of working on like harmonizing all of those records because, this one was on a location where maybe the land was subsiding or rising, because we're pulling water out of the ground or whatever it may be. It's a huge scientific endeavor to do this, and I'm in awe of it. I'm more on the satellite end of things where it's easy. It's expensive but easy. So let me transition to health. And I know, Lori, we talked about like 40 minutes of talking, 20 minutes of Q&A. I'll try to retain like a good 10 minutes for Q&A here, but
And
keep
we've been
asking.
doing some Q
Yeah,
in the intermediate, so don't worry
exactly.
about it too much. Yeah.
And keep interrupting as you have questions, but so I just wanted to share that, it's kind of I never would have predicted this happening in my career 10 years ago, actually. It wasn't even really intentional. I'm a physical climate scientist. I learn about the laws of physics and I apply them to the motions of the atmosphere and the ocean and like where the heat's going. And that's all I was ever interested in. And then I started at CU Boulder in 2015 and we got a call from some medical doctor over at our medical campus in the other side of Denver. He's a kidney doctor and he's like, we're really interested in climate change over here, but we don't know what we're doing. Do you have are you interested in collaborating on climate impacts on health? And I was like, I don't know. Sure. And so we all hit it off and we started developing these projects. And I think now I can kind of say like a third of my research program is dedicated to climate and health, which is pretty funny because one day I'll be writing this esoteric paper about, ocean waves or something, and then the next day it's like mosquitoes and how they are transmitting diseases and how that depends on the environment. But there's that connection to the environment that I think is really interesting. And we know about this. It's one of the many ways in which climate change is definitely impacting and will continue to impact human health. So where I've kind of spent more of my energy on this is in the vector-borne diseases category. And that just means, you've got the environment and then you've got some vector living in the environment, like a mosquito, and the mosquito then transmits it to a person. This is as opposed to like heat or wildfire, smoke exposure, things like that. There's no intermediary vector. It's just like you're exposed to the bad thing straight away. So vectors are complicated, but they're actually interesting from an environmental standpoint because, mosquitoes, they like standing water. So it's kind of part of it is the basic premise of it is pretty simple. The more water sitting around, the more mosquitoes. And then there's all the socioeconomic factors like that mitigate your exposure to mosquitoes. Can you afford, bed nets and all these kinds of things? But um, malaria is kind of where I've spent a lot of my time thinking about this. These are not my papers, but there are a whole bunch of papers that have been warning us that our exposure to vectors such as mosquitoes. This is a Aedes aegypti mosquito, and that's the one that transmits dengue, Zika, yellow fever, chikungunya. This one transmits a lot of bad things. Um, and there's an interesting study that shows the predicted expansion, the historical and the predicted expansion of the Aedes aegypti mosquito habitat in the southeastern U.S. over time, and how it depends on whether we emit a lot of carbon dioxide and warm up the world a lot, or just a little bit of carbon dioxide. And it depends a lot on how rainfall changes, which is often really uncertain and more complicated than just temperature. But most of my work has been focused on southeastern Africa, Malawi, and Mozambique. I had a PhD student a few years ago who finished up. A lot of his work was looking at malaria in Mozambique, which is this big coastal country in southeastern Africa, alongside the Indian Ocean here. And then more recently, Malawi, which is landlocked, but it's got a big lake running right down the eastern side of Malawi, Lake Malawi. And so there's water there too. There's a lot of water, and it has a very distinct wet season. So to really quickly summarize, I will avoid the details. I put way too much detail in these slides, but we looked at, what this often comes down to is a common, sort of a serendipitous, frankly, overlap of people who have the right data. So health data is really hard to get. In the US, it's like next to impossible to actually get what you really need when you need it, because of privacy things. But internationally, it's a lot easier. The regulations are more relaxed, let's just say, but where do you go and find it? You don't have something like you have in the US with some central repository of all the health data. You just literally have to know the guy who's like the minister of health in this district over here, and kind of have some connections and work those. And so I mean, that's kind of how this one happened. We had personal research connections with people in Mozambique. Uh, this fellow James Colburn, he works for the Clinton Health Access Initiative, and he had been working in Mozambique for a long time. We had these connections. And so from a climate science standpoint, it's really fun to take these records. I'll show an example of a record over here, and this is not kind of representing how sophisticated some of the analysis is, but it's amazing what you find when you take these unique, as long as they're reliable, records of health outcomes from diseases, and you match them up with climate things. My sort of not pet peeve, but I don't know, the thing that I'm always kind of like, yeah, uncomfortable with is how much sometimes we rely on the seasonal cycle of things. Like, it's really obvious when you look at this that shortly after the annual increase in precipitation in this particular district of Mozambique, you've got the onset of the malaria season. Well, duh, of course, that doesn't mean you're going to be able to predict it, right? I mean, you're going to be able to predict, yes, every summer we're going to get rain and we're going to get malaria, but that doesn't mean you can predict that next year will be an unusually bad malaria season, and so that's what we're going towards. We're trying to leverage semi-predictable things in the climate system with lead times of maybe a year to to predict whether or not you're going to have a particularly bad malaria season next year, relative to like the average. And so for that, we often turn to the ocean, and I'll just show this. You know what? So what I'm going to do is I'm going to demonstrate the point that I just made, but I'm going to use Malawi. So Malawi is so I'm kind of being mindful of the time here. Malawi, if we take it's like the same data. It's counts and incidence rates of malaria in the country. So if I take, do a principal component analysis on the cases. These black curves are the first and second principal components, meaning like they kind of represent the majority of the variability over time of cases. It's like you take the whole messy record, without going into the details of principal component analysis or EOF analysis. It's like almost like the original machine learning, if you think about it. It takes the big data sets and it says, what are the recurrent patterns that happen in this data set? What are the most important recurring patterns, and throw everything else out. And then let's see if we can actually explain these important recurring patterns. So that's what is here in the black curves, the first principal component and the second principal component. And by construction, they're going to be uncorrelated. Well, anyways, if we take those and then we go to the global ocean temperatures and say, show me by way of a correlation map, show me what the ocean looks like when the first principal component of malaria cases is high versus when it's low. It actually led us to the Atlantic Ocean. And it says, okay, well, when the Atlantic Ocean is warm right here, we have lots of malaria cases in Malawi. And then for the second principal component, we did the same thing. But for the second principal component, it was the Indian Ocean that actually lights up as being most important. And this is great news for trying to predict malaria, because it's really hard to predict the weather 30 days in advance or something like that. But the ocean moves slowly. The tropical Atlantic doesn't just like flip-flop from cold to warm on like a weekly basis. These are slowly evolving patterns because, again, the ocean's got all that thermal capacity. It's really hard to change it too quickly. So as the ocean changes, we're actually able to explain, I would not say predict yet, but that's what we're kind of where we're going in our work. We can explain the actual preponderance of the malaria cases based on the variability in the nearby oceans. And you might be wondering, what the heck does the temperature of the ocean all the way over there in the Indian Ocean or the Atlantic Ocean have to do with malaria? Well, the ocean is felt by the atmosphere. When it's hot in the tropics, for example, when the ocean's warm, hot air rises. That's got to go somewhere. That changes the whole atmospheric circulation pattern. Kind of like in an old house. I've used this analogy before today. In an old house with a radiator on a cold day. Imagine you turn that on. You're gonna set up these air currents around your house, right? Say you then move that radiator to a different room somehow. That's going to change the whole, air current pattern in your house. And that's what's happening as these ocean patterns, it gets warm and cold here, but these are slowly evolving, which means they are somewhat predictable patterns. Got a question here. Why high and low? Are you talking about the SST, the ocean
Yeah.
patterns? Oh, I
Yeah,
see.
and that's have to do with what the different components really represent, right? So one
Exactly.
is correlated with the hot. What are those different components and how?
Yeah, I'm skipping some of the how the yeah.
It's okay.
Let's just say that you could flip the sign. I think this might help. You could, if you changed all of the blues on the map to red and all the reds to blues, all you got to do is take these and flip them upside down. It applies in both directions. It doesn't really have anything to do with like coldness or warmness per se. They're kind of symmetric in their impact. Okay. I think that was probably getting at what you were talking about. Oh, and one last thing I want to say is that it's really been useful to go beyond, even for the local surface climate. We think of like temperature, precipitation, things like that. Well, we now have the ability to measure from space soil moisture. And that's because the more water locked up in the soil, the more gravitational pull it has, the more mass it has. And there's a satellite that orbits the Earth that measures exactly that, the gravitational pull of the ground beneath it. So there's a satellite called GRACE, and we can measure soil moisture. It turns out if we have soil moisture, we can reconstruct pretty closely the combination, even the combination of the two principal components of malaria using soil moisture. Soil moisture is great because rainfall doesn't necessarily mean there's going to be more standing water. What if it's really hot? If it's really hot, it evaporates, right? And so that kind of comes to the my last slide here, which is the future. And this is for Malawi, for example, but we're looking at global climate model projections of soil moisture. So here's how you read this. This is Malawi. And this is the prediction of change in soil moisture in the future relative to historical. And brown means it's going to get dry. So that you would think that would be really good. That should be good, actually, if you're worried about malaria, because less standing water around, that's not good for mosquitoes. And same thing for a higher emission scenario. But anyways, and this is just a time series of it, and it shows sort of a subtle decline in soil moisture over time. And it's kind of insensitive to it happens regardless of whether we emit a lot of CO2 or a little CO2. But what's interesting is you would get a very different answer, or you just a different answer if you just looked at precipitation. So this is a map combining 33 different global climate models predicting rainfall change in the future, sort of like end of the century relative to now. You can think of it like that. Green means more rainfall, brown means less rainfall. And I've just used a little shape in PowerPoint to outline where Malawi is. It's not actually that shape, but that's where Malawi is. And what's going on there is a whole nothing burger. The diagonal lines, that means no change or no robust signal. It means either there's no change or the models don't agree on whether it's going to increase or decrease. And so, why do you think, this is an open question to you, why do you think that even though there's no robust predicted change in rainfall, why would soil moisture go down in the future? If it's not happening because of a decrease in rainfall. Any ideas? It's temperature. So of course it's going to warm up. Like under both of these scenarios, it's going to warm up. So the warming makes more evaporation of the water. So my closing points here, even though this is classic me, I skipped a lot, but I've seen a lot of evidence from my work and a lot of other people's work that climate variability from seasonal to decadal timescales influences malaria dynamics in Southeast Africa and many other places. It's important to try to stretch beyond the, sort of standard local variables. Look at things like soil moisture that are more directly related to, in this case, the vector being the mosquitoes, nearby ocean temperatures, and then like large scale atmospheric things that help you actually understand the mechanism for why does the Atlantic Ocean have any connection to Africa? There's a connection, and it's important to understand it if you want to have confidence in the predictions. Um, and then I'll just go to my last point here. In my years of doing this so far, I've seen the field come closer and closer to actually co-developing the research questions from day one in collaboration between the climate scientists and the people who really have the ideas. Like, I don't know a lot of climate scientists who sit around and just would think, I wonder, about like this mosquito, or, there's all these people in public health and medicine who already studied things like chronic kidney disease or malaria, right? And it's like the ideas are generally coming from that direction. They're like, well, how is the climate going to impact this thing that I've dedicated my life to understanding? That's where it's coming from. But I've seen the proposals get so much better when sort of like how we're going to approach the problem, what data sets are we going to use, what are the uncertainties going to be, if it's really done co-developed in tandem with the climate scientists. I haven't had a case where I've had like, hey, our proposal, to the NIH is due next week. Can you give me a letter of support? I haven't seen that in a while. It's been more like, hey, I got a deadline in 6 months. Let's start, daydreaming about this together. So that's a good thing I see, and I wanted to keep going in that direction. So I will close there. Sorry for going right up to the hour here, but happy to.
Kris, this is fantastic. I am, and I'll say the social science community feels the same about interdisciplinary work. We were often the last ones to the table, and you see that last, which is really nice too. This has been fantastic. Yeah. So we did put in the chat an email, our general email address for Cash. If you do have questions for Kris, maybe we can try to get them answered via email. And there's also a survey. We really would love your input in terms of this. And I wanted wanted to say too, Kris, one thing that I think would be really helpful, and we don't have time for it now, but maybe we communicate with people, is how do we find those climate scientists that are interested in working and collaborating with us? So let's talk about that and strategize and communicate with our community, because it's a big part of what the Center for Aging, Climate, and Health is working on. So. All right, everybody, we're at time, so we will probably head out, but please do. Oh, yes, thank you, Julia. I forgot to mention we have a seed grant call out. It requires integration of environmental and social, so here's a chance to find your climate scientist. And you'll also soon see a call out for opportunities to share code. So, and then sign up for our newsletter if you haven't yet done that. But yes, Kris, this has been fascinating. I've learned so much. And everybody follow up if you have